Is roughness average approximately 2 micrometers truly enough? Cell-level nanostructure is the next standard. Almost every implant manufacturer today targets a roughness average of around 2 micrometers and presents it as the ideal surface roughness for osseointegration. It has become the industry standard. But how did we get here? And more importantly, is it actually right? To answer that, we need to go back to where implant surface science began. The early Brånemark system used a pure titanium rod, simply turned on a lathe. We called it a machined surface. It formed a titanium oxide layer through contact with atmospheric oxygen, and through that layer, osseointegration was believed to occur. However, machined surfaces had biologic limitations. Albrechtson and colleagues showed that implant success was heavily influenced by bone quality and implant bed conditions. Adele and colleagues confirmed long-term stability was possible. In other words, machined surfaces alone could not achieve reliable osseointegration in poor quality bone. TPS, HA coating, sintered porous surfaces were all introduced to drive stronger bone response. Roughened surfaces induced significantly stronger osseointegration than machined ones. Once these excessively rough surfaces were exposed to the oral environment, plaque-induced contamination triggered bone loss that was rapid and hard to control. The direction reversed. The focus shifted to moderately rough surfaces, rough enough to outperform machined surfaces, but controlled enough to reduce biologic risk. Zimmer Biomet's double acid etching, BioHorizons RBM, Straumann's SLA, Nobel Biocare's anodizing. These surfaces, generally in the range of 1 to 3 micrometers roughness average, delivered faster osseointegration with far fewer complications. Cochrane and colleagues reported that a controlled SLA surface outperformed TPS in bone apposition and BIC, with a more favorable long-term response. Wennerberg and Albrechtson then synthesized the existing evidence and concluded that a moderately rough surface at SA 1 to 2 micrometers was most closely associated with optimal bone response. And with that, roughness average approximately 2 micrometers became the standard. Implant surface science largely stayed there. Is RA approximately 2 micrometers alone truly enough? Was the moderately rough standard built on osteoblast biology or on clinical compromise? To be precise, the roughness average concept was less about osteoblast biology and more about finding a compromise. Faster osseointegration than machined surfaces, fewer complications than excessively rough ones. Anselm showed that osteoblast adhesion is governed not just by roughness, but by surface topography, chemistry, and surface energy. Zhao and colleagues demonstrated that surfaces with identical titanium microstructure could produce different osteoblast differentiation and activity, simply based on differences in surface energy and hydrophilicity. The industry recognized this and began looking beyond roughness average, exploring surface chemistry and hydrophilicity to enhance biologic activity. Two surfaces with the same roughness average value can behave very differently at the biologic level. To truly understand what the next generation of implant surfaces should look like, we need to go further and examine what osteoblasts are actually doing at the cellular level. Osteoblasts are 10 to 30 micrometers in size, but during adhesion and differentiation, they extend philopodia, slender actin-based processes, roughly 100 to 500 nanometers in diameter, reaching up to 5 to 20 micrometers in length to probe and attach to the implant surface. At the very tip of each extension, a contact interface of approximately 100 to 1000 nanometers is formed. This is where integrin-mediated focal adhesion activates, where actin cytoskeletal organization occurs, and where the cell decides whether to adhere, spread, and differentiate. Webster and colleagues reported increased osteoblast adhesion on nanophase metal surfaces versus conventional ones, and showed that nanostructured surfaces forming calcium titanate produced greater adhesion than pure HA or titanium surfaces alone. Dalby and colleagues demonstrated that even among surfaces with identical nanoscale dimensions, differences in nanoscale organization alone were enough to alter osteogenic differentiation, indicating that nanoscale structure matters even when microscale roughness looks the same. What osteoblasts are actually responding to is not 2 micrometer roughness. It is the nanoscale interface, and that is a level roughness average simply cannot describe. This is the gap that MegaGen set out to address when developing the X-Speed surface in 2012. X-Speed maintains an SLA-based moderately rough surface at approximately 2 micrometers roughness average, consistent with the established standard, but it simultaneously forms a uniform calcium titanate nanostructure at approximately 200 to 300 nanometers scale. The goal is to provide an interface where osteoblast filopodia can make contact more readily and establish more stable anchorage by designing the surface at the scale the cell actually operates. Whether 200 to 300 nanometers is the definitive ideal value requires further research, but studies have reported that this nanoscale modified surface increases osteoblast differentiation and activity by approximately 2.5 times compared to conventional SLA surfaces. On the same SLA-based, moderately rough foundation, the X-Speed surface demonstrated a higher mineral apposition rate, leading to greater bone-to-implant contact at both 4-week and 6-week healing intervals. Even in soft cancellous bone environments such as the posterior maxilla, faster peri-implant bone formation and earlier osseointegration have been reported. Roughness average, approximately 2 micrometers, was a meaningful standard. It moved the field forward, and it did so with clinical evidence behind it. But a standard built on clinical compromise is not the same as a standard built on biology. If osteoblasts are operating at the nanoscale, then that is where implant surface design needs to be. The question is no longer just how rough the surface is. It is what that surface looks like to the cell that matters. Beyond roughness average, cell-level nanostructure is the next standard.